In game theory, the Nash equilibrium is a solution concept of a non-cooperative game involving two or more players, in which each player is assumed to know the equilibrium strategies of the other players, and no player has anything to gain by changing only their own strategy. If each player has chosen a strategy and no player can benefit by changing strategies while the other players keep theirs unchanged, then the current set of strategy choices and the corresponding payoffs constitutes a Nash equilibrium. The reality of the Nash equilibrium of a game can be tested using experimental economics method. Stated simply, Amy and Will are in Nash equilibrium if Amy is making the best decision she can, taking into account Will's decision while Will's decision remains unchanged, and Will is making the best decision he can, taking into account Amy's decision while Amy's decision remains unchanged. Likewise, a group of players are in Nash equilibrium if each one is making the best decision possible, taking into account the decisions of the others in the game as long as the other party's decision remains unchanged. Applications. Game theorists use the Nash equilibrium concept to analyze the outcome of the strategic interaction of several decision-makers. In other words, it provides a way of predicting what will happen if several people or several institutions are making decisions at the same time, and if the outcome depends on the decisions of the others. The simple insight underlying John Nash's idea is that one cannot predict the result of the choices of multiple decision-makers if one analyzes those decisions in isolation. Instead, one must ask what each player would do, taking into account the decision-making of the others. Nash equilibrium has been used to analyze hostile situations like war and arms races, and also how conflict may be mitigated by repeated interaction. It has also been used to study to what extent people with different preferences can cooperate, and whether they will take risks to achieve a cooperative outcome. It has been used to study the adoption of technical standards, and also the occurrence of bank runs and currency crises. Other applications include traffic flow, how to organize auctions, the outcome of efforts exerted by multiple parties in the education process, regulatory legislation such as environmental regulations, analyzing strategies in marketing, and even penalty kicks in football. History. The Nash equilibrium was named after John Forbes Nash, Jr. A version of the Nash equilibrium concept was first known to be used in 1838 by Antoine-Augustin Cournot in his theory of oligopoly. In Cournot's theory, firms choose how much output to produce to maximize their own profit. However, the best output for one firm depends on the outputs of others. A Cournot equilibrium occurs when each firm's output maximizes its profits given the output of the other firms, which is a pure strategy Nash equilibrium. Cournot also introduced the concept of best response dynamics in his analysis of the stability of equilibrium. However, Nash's definition of equilibrium is broader than Cournot's. It is also broader than the definition of a Pareto-efficient equilibrium, since the Nash definition makes no judgments about the optimality of the equilibrium being generated. The modern game theoretic concept of Nash equilibrium is instead defined in terms of mixed strategies, where players choose a probability distribution over possible actions. The concept of the mixed strategy Nash equilibrium was introduced by John von Neumann and Oscar Morgenstern in their 1944 book The Theory of Games and Economic Behavior. However, their analysis was restricted to the special case of zero-sum games. They showed that a mixed strategy Nash equilibrium will exist for any zero-sum game with a finite set of actions. The contribution of Nash in his 1951 article Non-Cooperative Games was to define a mixed strategy Nash equilibrium for any game with a finite set of actions and prove that at least one Nash equilibrium must exist in such a game. The key to Nash's ability to prove existence far more generally than von Neumann lay in his definition of equilibrium. According to Nash, An equilibrium point is an n-tuple such that each player's mixed strategy maximizes his payoff if the strategies of the others are held fixed. Thus each player's strategy is optimal against those of the others. Just putting the problem in this framework allowed Nash to employ the Kakutani fixed point theorem in his 1950 paper, and a variant upon it in his 1951 paper used the Brouwer fixed point theorem to prove that there had to exist at least one set of mixed strategies that mapped back into themselves for non-zero-sum games. Namely, a set of strategies that did not call for a shift in strategies that could improve payoffs. They have proposed many related solution concepts designed to overcome perceived flaws in the Nash concept. One particularly important issue is that some Nash equilibria may be based on threats that are not credible. In 1965, Reinhard Selten proposed subgame perfect equilibrium as a refinement that eliminates equilibria which depend on non-credible threats. Other extensions of the Nash equilibrium concept have addressed what happens if a game is repeated, or what happens if a game is played in the absence of perfect information. However, subsequent refinements and extensions of the Nash equilibrium concept share the main insight on which Nash's concept rests. All equilibrium concepts analyze what choices will be made when each player takes into account the decision-making of others. Definitions. Informal definition. Informally, a set of strategies is a Nash equilibrium if no player can do better by unilaterally changing their strategy. To see what this means, imagine that each player is told the strategies of the others. Suppose then that each player asks themselves, knowing the strategies of the other players, and treating the strategies of the other players as set in stone, can I benefit by changing my strategy? If any player could answer yes, then that set of strategies is not a Nash equilibrium. But if every player prefers not to switch, then the set of strategies is a Nash equilibrium. Thus, each strategy in a Nash equilibrium is a best response to all other strategies in that equilibrium. The Nash equilibrium may sometimes appear non-rational in a third-person perspective. This is because it may happen that a Nash equilibrium is not Pareto optimal. The Nash equilibrium may also have non-rational consequences in sequential games because players may threaten each other with non-rational moves. For such games, the subgame perfect Nash equilibrium may be more meaningful as a tool of analysis. Let be a strategy profile of player and be a strategy profile of all players except for player. When each player chooses strategy resulting in strategy profile, then player obtains payoff. Note that the payoff depends on the strategy profile chosen, i.e., on the strategy chosen by player as well as the strategies chosen by all the other players. A strategy profile is a Nash equilibrium if no unilateral deviation in strategy by any single player is profitable for that player. That is when the inequality above holds strictly for all players and all feasible alternative strategies. Then the equilibrium is classified as a strict Nash equilibrium. If instead, for some player, there is exact equality between and some other strategy in the set, then the equilibrium is classified as a weak Nash equilibrium. A game can have a pure strategy or a mixed Nash equilibrium. Nash's existence theorem. Nash proves that if we allow mixed strategies, then every game with a finite number of players in which each player can choose from finitely many pure strategies has at least one Nash equilibrium. Examples. Coordination game. The coordination game is a classic two-player, two-strategy game, with an example payoff matrix shown to the right. The players should thus coordinate, both adopting strategy A, to receive the highest payoff, i.e., if both players chose strategy B, though, there is still a Nash equilibrium. Although each player is awarded less than optimal payoff, neither player has incentive to change strategy due to a reduction in the immediate payoff. A famous example of this type of game was called the Stag Hunt. In the game, two players may choose to hunt a stag or a rabbit, the former providing more meat than the latter. The caveat is that the stag must be cooperatively hunted, so if one player attempts to hunt the stag, while the other hunts the rabbit, he will fail in hunting, whereas if they both hunt it they will split the payload. The game hence exhibits two equilibria, and hence the player's optimal strategy depend on their expectation on what the other player may do. If one hunter trusts that the other will hunt the stag, they should hunt the stag. However, if they suspect that the other will hunt the rabbit, they should hunt the rabbit. This game was used as an analogy for social cooperation, since much of the benefit that people gain in society depends upon people cooperating and implicitly trusting one another to act in a manner corresponding with cooperation. Another example of a coordination game is the setting where two technologies are available to two firms with comparable products, and they have to elect a strategy to become the market standard. If both firms agree on the chosen technology, high sales are expected for both firms. If the firms do not agree on the standard technology, few sales result. Both strategies are Nash Equilibria of the game. Driving on a road against an oncoming car, and having to choose either to swerve on the left or to swerve on the right of the road, is also a coordination game. For example, with payoffs 10 meaning no crash and 0 meaning a crash, the coordination game can be defined with the following payoff matrix. In this case there are two pure strategy Nash Equilibria, when both choose to either drive on the left or on the right. If we admit mixed strategies, then there are three Nash Equilibria for the same case. Two we have seen from the pure strategy form, where the probabilities are for player 1, for player 2, and for player 1, for player 2 respectively. We add another where the probabilities for each player is they can cooperate by not snitching, or defect by betraying the other. However, there is a catch. If both players defect, then they both serve a longer sentence than if neither said anything. Lower jail sentences are interpreted as higher payoffs. The prisoner's dilemma has a similar matrix as depicted for the coordination game, but the maximum reward for each player is obtained only when the players' decisions are different. Each player improves their own situation by switching from cooperating to defecting, given knowledge that the other player's best decision is to defect. The prisoner's dilemma thus has a single Nash equilibrium, both players choosing to defect. What has long made this an interesting case to study is the fact that this scenario is globally inferior to both cooperating. That is, both players would be better off if they both chose to cooperate, instead of both choosing to defect. However, each player could improve their own situation by breaking the mutual cooperation, no matter how the other player possibly changes their decision. Network traffic. An application of Nash equilibria is in determining the expected flow of traffic in a network. Consider the graph on the right. If we assume that there are cars traveling from A to D, what is the expected distribution of traffic in the network? This situation can be modeled as a game, where every traveler has a choice of three strategies, where each strategy is a route from A to D. The payoff of each strategy is the travel time of each route. In the graph on the right, a car traveling via experiences travel time of, where is the number of cars traveling on edge. Thus, payoffs for any given strategy depend on the choices of the other players, as is usual. However, the goal in this case is to minimize travel time, not maximize it. Equilibrium will occur when the time on all paths is exactly the same. When that happens, no single driver has any incentive to switch routes, since it can only add to their travel time. For the graph on the right, if, for example, 100 cars are traveling from A to D, then equilibrium will occur when 25 drivers travel via, 50 via, and 25 via. Every driver now has a total travel time of 3.75. Notice that this distribution is not, actually, socially optimal. If the 100 cars agreed that 50 travel via and the other 50 through, then travel time for any single car would actually be 3.5, which is less than 3.75. This is also the Nash equilibrium if the path between B and C is removed, which means that adding another possible route can decrease the efficiency of the system, a phenomenon known as Bayes' paradox. Competition game. This can be illustrated by a two-player game in which both players simultaneously choose an integer from 0 to 3 and they both win the smaller of the two numbers in points. In addition, if one player chooses a larger number than the other, then they have to give up 2 points to the other. This game has a unique pure strategy Nash equilibrium, both players choosing 0. Any other strategy can be improved by a player switching their number to 1 less than that of the other player. In the table to the right, if the game begins at the green square, it is in player 1's interest to move to the purple square and it is in player 2's interest to move to the blue square, although it would not fit the definition of a competition game. If the game is modified so that the two players win the named amount if they both choose the same number, and otherwise win nothing, then there are 4 Nash equilibria, and Nash equilibria in a payoff matrix. There is an easy numerical way to identify Nash equilibria on a payoff matrix. It is especially helpful in two-person games where players have more than 2 strategies. In this case, formal analysis may become too long. This rule does not apply to the case where mixed strategies are of interest. The rule goes as follows. If the first payoff number, in the payoff pair of the cell, is the maximum of the column of the cell and if the second number is the maximum of the row of the cell, then the cell represents a Nash equilibrium. We can apply this rule to a 3x3 matrix. Using the rule, we can very quickly see that the Nash equilibria cells are, and indeed, for cell 40 is the maximum of the first column and 25 is the maximum of the second row. For 25 is the maximum of the second column and 40 is the maximum of the first row. Same for cell. For other cells, either one or both of the duplicate members are not the maximum of the corresponding rows and columns. This said, the actual mechanics of finding equilibrium cells is obvious. Find the maximum of a column and check if the second member of the pair is the maximum of the row. If these conditions are met, the cell represents a Nash equilibrium. Check all columns this way to find all Ni cells. An n times n matrix may have between 0 and n times n pure strategy Nash equilibria.